Hi everyone. In this video, we're going to cover section 2.2, the limit of a function. And before I define formally what a function is, I want to take a look at these three graphs and just kind of investigate where the idea comes from. All right. And so if you look at each of the three graphs, f of x, g of x, and h of x, we're looking at an x value of 2. What's going on when x is 2 for each of these three graphs? Now, the first thing to notice is that at exactly 2, none of the functions are defined. There's an open circle there, we have open circles here and here, and there is no point when x is 2. So for any of the three functions, at 2, the function is undefined. So introduce talking about a limit, what we're going to think about is what happens in each of the three graphs as x gets closer to 2. So when we talk about limits, we're looking at at this x coordinate, in this case 2, at this x coordinate, what happens with the y coordinate? All right, so when x is 2, what is my y coordinate? Well, it's not 1, 2, 3, 4. It's not 4. But as we get closer and closer to 2 from this side and from the other side, the y values are getting closer and closer to 4. So like when x is 1, y is 3. When x is 1.5, y looks like it's 3.5. When x is 1.9, it looks like y is 3.9. Getting closer and closer to 2. Coming from above, when x is 3, y appears to be, I think, 5. When x is 2.5, we got about 4.5. When x is 2.1, we got about 4.1. So it looks like our y coordinate, and I can draw arrows on this graph maybe, it looks like our y coordinates are getting closer and closer to a y value of 4. All right, compare that to the other graph, right? When x is 2 and we're a little bit below, right? We're at negative, there's not a line there, but I think it's -1, -1, -1, -1, -1, -1. As you get closer and closer to 2 from one side, and as you get closer and closer to 2 from above, right, it looks like we're up at +1 the whole way. At exactly 2, we're not defined, but we've got two different things going on, whether we're going from above 2 or below 2 as we get closer. And that's the idea with limits, is we're getting ever infinitely closer to the x value of 2. So 3, 2.5, 2.1, 2.01, 2.001, etc., getting closer and closer to 2. All right, and then on the third one, h of x, right, as you get closer to 2, right, it looks like the graph blows up. At like 1, we're here. At 1.5, we're here. At 1.8, we're here. At 1.9, we're even higher. Same deal from above. As you get closer to 2, you're getting these really, really, really big y coordinates, getting ever infinitely larger. Okay, it looks like they're approaching infinity. Okay, it looks like those y coordinates blow up, both from above and below 2. They blow up to positive infinity. Okay, and so the notation that I want to introduce on this slide, and then we'll formally define on the left side, is specifically about the first graph. All right, and so what we say is we're going to say the limit. So we abbreviate limit, LIM. Underneath the word limit, we write x and then an arrow, that's an arrow, and then a 2. And so the way that we read that out loud is the limit as x approaches 2. So let me write that down. That is read verbally as the limit as x approaches 2. That's a t at the beginning. The limit as x approaches 2. And then we write our function of f of x. So I'll put that above here in quotes too, of f of x. And then, well, it looks like our limit is equal to 4, right? That was the y coordinate that we were approaching above and below. The limit as x approaches 2 of f of x is equal to 4. Okay, and so that's the notation that we're going to use. The word limit, is like normal sized. The as x approaches 2 is like a scooch smaller, just a little bit smaller than the normal writing. F of x is normal sized on the line, and then equals 4 is normal sized on the line. Okay, so now let's scroll down here and zoom in a little bit. There we go. So here we have our formal definition from our text of limit. So it says let f of x be a function defined at all values in an open interval containing the number a, with possible exception of a itself. So that means that it doesn't matter what's happening at exactly 2. It can be an open circle. It matters what's happening around 2 as you get closer to 2. And let L be a real number. So L we're using for what the limit is. If all values of the function f of x approach the real number L as the values of x, they don't have to be equal to a, approach the number a, then we say that the limit of f of x as x approaches a is L. And then it says more succinct, so we're trying to like simplify our language here. As x gets closer to a, f of x gets closer and stays close to L. And so I think in terms of like understanding what we're talking about here, this more succinct thing is what's going to be the most helpful. As x gets closer to our number, f of x gets closer to the limit. All right? And then symbolically, this is what I wrote above. The limit as x approaches a of f of x is equal to L. Now, the first technique that we use in understanding and evaluating limits is a table of values, a table, limits using a table. Okay, so if I want to know what is the limit as x approaches 4 of that function that's after it, right, the first thing that I can do is create a table. And so the way that I'm going to make my table is horizontally, and I'm going to go x up here, f of x down there, and in the middle of my table, I'm going to put 4, okay? And if you try to evaluate 4 in that function, the square root of 4 is 2, minus 2, I get 0 in the numerator. 4 minus 4, I get 0 in the denominator, 0 over 0, not defined, okay? So this 4 does not exist, and that's okay. I want to know what happens as I get closer and closer and closer to 4. So for this problem, below, I'm going to plug in 3, 3.5, 3.9, and 3.99. All 4 of those numbers. And then above, I'm going to plug in, substitute 5, 4.5, 4.1, and 4.01. And now I'm just going to use my calculator and chug through each of these, 8 different substitutions. First one up, when I plug in 3, I'm doing this in my calculator. I'm being super careful with all of my parentheses, but I get decimal point 2679 in my calculator. So I'm going to round that to 0.268. 0.2679, I'm going to round it to 0.268. All right, next up I have when I evaluate 3.5 in my function, this one I got 0.258, so decimal point 258, and it's a 3 after the 8, so it naturally rounds down. Next up, when I evaluate 3.9, I get decimal point 2515, so 252. And then finally, when I substitute 3.99, I get 0.25015, etc., etc., etc. Okay, so it looks like 0.26, 0.258, 0.252, 0.250, we're decreasing and getting closer to maybe a quarter, 1/4. That's the idea. Now let's see what happens when we start above. I'm going to plug in 5 first. And when I do that, I get 0.236. Substitute 4.5, and I get 0.2426. Oops, so that should be 24. Let's make that 2 and 2 look like a 3. There we go, 243. Substitute 4.1, and I got 0.248, 0.248. And finally, when I substitute 4.01, I get 0.2498. When I round that like I've been rounding, that's going to bump it up to 0.250. Okay, so it looks like when I get closer and closer to 4, from both below and from above, it looks like we're getting closer to 1/4. Moving forward, we'll have more precise procedures, but the first step in understanding what's going on is by just evaluating numbers, literally getting closer and closer to what your limit is. All right, in this next example, let's take a look at how we find limits using just the graphs of the function. All right, and so for this first one here, we are told to find the limit as x approaches 1, as x approaches -1 of g of x. So I'm looking at my g function. Here is -1. So as the x coordinate gets closer to -1 from above and gets closer to -1 from below, where is f of x, right? So if I were to plug in -0.5, right, I'd be up here. -0.9, I'd be up here. If I were to plug in -1.5, I'd be up here. -1.01, I'd be up here, right? As you get closer and closer to -1, the graph is getting closer to that number, which is 1, 2, 3. So this limit is equal to 3. Notice it didn't matter where g of x was at exactly -1. If the question asked you what is g of -1, the answer is 1, 2, 3, 4. The answer is 4. At -1 exactly, your y coordinate is 4. But as you get closer to -1, from the left, from the right, then the function gets closer and closer to 3. Moving over to this other problem, right? In here, we're looking at h of x, and what is the limit as x approaches 2 of h of x. So I'll write the limit as x approaches 2, that's supposed to be an arrow, of h of x is equal to, and then let's take a look. Here's 1, here's 2. So as I approach 2 from the left, we're going in that direction on the graph. From the right, we're looking at it from this direction, and it sure looks like we're getting closer and closer to a y coordinate of -1. So that's how we can use graphs to evaluate limits. Now we'll just briefly talk about two important limits and one that doesn't exist. All right, so first, the important limits. The first one, the limit as x approaches a of x is equal to a. I like to think about this with numbers instead. The limit as x approaches, let's say, 3 of x is equal to 3. So why is that? Here, my function is f of x equals x, or y equals x, right? What that graph looks like, that's like the 45-degree line. That's the points on this function are 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. Okay, so as x gets closer to this coordinate, y gets closer to that exact same coordinate, because it's just that 45-degree line. The points are 1, 1, 2, 2, 3, 3, 4, 4, as I said. And then the second one, the limit as x approaches a of c equals c. Let's throw some numbers in there instead. The limit as x approaches, let's use 3 again. I'm going to pick a different number for the c, though, of 4 is equal to 4. Okay, so for this one, it's a little bit more, maybe not abstract, but you got to think a little bit more before understanding what this one means. Okay, here my function, the function is 4. F of x equals 4. All right, so what does that look like? If I draw a quick xy axis, f of x equals 1, 2, 3, 4. That is a horizontal line. A horizontal line. F of x equals, 4, like that. There we go. There's my parentheses. All right, so the limit as x approaches 3, 1, 2, 3 on the x-axis. Well, where's the graph? It's up at 4. How about as x approaches 5? Where's the graph? Hey, it's up at 4. What about at negative 4? Hey, the graph is up at 4. So the limit of a constant function is that constant. Because it's a horizontal line, the y-coordinate never changes. All right, now let's scroll down here and take a look at a limit that we can say does not exist. All right, now you should see that a table has magically appeared on the screen, right? So this is the table that we're going to create in order to understand what's going on in this problem and why it doesn't exist. So the first thing to kind of make a note of is that at 0, at exactly 0, inside of that parentheses, 1 divided by 0, that is not defined, okay? So our limit doesn't exist at exactly 0. excuse me, the function doesn't exist at exactly 0 because 1 over 0 is undefined. All right. But what happens as we get closer to 0 from above, and what happens as we get closer to 0 from below? If you want to try substituting any of these into your calculator, pause the video now because all of the answers are about to magically pop on the screen. Okay, so there they are. All my answers are on here. The grid's filled in. Okay, so let's take a look and analyze this. Notice first that those three numbers and those three numbers are the same. That's fine, but that doesn't help this limit to exist, right? For the limit to exist, from above, from below, we have to be approaching the same value. I get negative a little more than a half, negative about a half, and then, boom, we're positive, right? It went negative, negative, positive from above. Positive 0.82. If you were to go even closer, if you were to go another like hundredth, a factor of 10th closer, it would flip back to negative again. All right, and then from below, a little more than a half, about a half, boom, we're negative. And then the same exact thing happens if you go, another factor of 1/10 closer. Okay, so there's no trend, right? Positive, positive, negative, 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 positive. We're not approaching a single value in this one. If you want to see an absolutely insane graph, make sure you go to the OpenStax, this example in OpenStax. This graph is really, really cool looking, and especially the action going on at 0 as you get closer to 0, it just kind of goes nutso. And that's because it goes quote-unquote nutso, not a formal mathematical term, just a Professor Carty term. That's why in this example, that limit that we're asked about, that limit, the limit, oops, I don't want my highlighter, scribble that out, the limit as x approaches 0 of the sine of 1 over x, that's an x, that does not exist. DNE does not exist because we're not approaching a single value. Alrighty, next up, we'll talk about one-sided limits, all right? And I'm not going to read these two different definitions for you. You can pause the video and read them for yourself. I'll just highlight, or I'll talk about the key aspect of them right here in our limit notation. What I'm kind of putting a box around, that is the limit as x approaches a from the left. That little negative sign from the left-hand side of that number, okay? And then for the second definition, that one is the limit as x approaches a from the right. If you don't know your left from your right, your left hand is the one that makes the L when you put up your index finger and your thumb, and your right hand is the one that looks like a backwards L. So if that helps, great. But that means, like, if you have a number line in front of you, from the left is the left-hand side of the number moving to the right, and from the right is the right-hand side of the number moving to the left. So from the left means this direction, from the right means that direction. A lot of the times we'll see one-sided limits and evaluate them when dealing with piecewise functions. So for this first example here, we have the limit as x approaches 2 from the left of f of x. And so the question is, which one is 2 from the left? Well, that's this piece right here. If x is less than 2, 1 is less than 2, that's from the left. Okay? So if x is less than 2, we're going to use the top piece of the function. That's this guy right here. So if I were to substitute in 1.9, 1.99, we can do that. Let me write it this way. F of 1.9 is 1.9 plus 1, 2.9. F, that's a squiggle, just kind of breaking it up. F of 1.99, 1.99 plus 1, 2.99, one more squiggle. F of 1.999, 1.999, add 1, 2.999. Does anyone have any guesses as to what our limit is? What are each of these function values getting closer to? 2.9, 2.99, 2.999. Don't everybody shout it out at once. The limit is equal to 3. The limit as x approaches 2 from the left of our function, that's f of x, is equal to 3. Boom. All right. How about as we approach 2 from the right? The right is, and I'll go with green here, if x is greater than or equal to 2. That is from the right. 3 is bigger than 2. 3 is to the right of 2. Okay, but I need to know what happens when I'm close to 2. So f of 2.1, that is 2.1 squared minus 4. Check that in your calculator and you get 0.41. Do my little squiggle again, just separating things here. F of 2.01, and that is 2.01 squared minus 4. For that one in my calculator, I got 0.0401. Okay, and then one more little squiggly line, f of 2.001, 0.001 squared minus 4. And I got in my calculator 0.004001. And for this one, it looks like our limit as x approaches, 2 from the right of f of x. Well, it looks like our decimals keep getting smaller and smaller and smaller, getting closer and closer and closer to 0. Okay, now so the relationship between these one-sided and two-sided limits is such that my limit, this is called the two-sided limit if there's no plus or minus sign after the a. The two-sided limit is L if and only if the limit from the left and the limit from the right are both L. So in order for the two-sided limit to exist, to be this number, the limit as we approach from the left and the limit as we approach from the right have to be that same number. So the one-sided limits have to be the same for the two-sided limit to exist. All right, now we get to talk about infinity. And that's one of my favorite things about calculus class, is that I get to regularly talk about things like infinities, and I just think that's totally awesome. All right, so there's a bunch of words on this slide. I'm going to zoom in and kind of just talk about the first definition, because the ones after it are all really, really similar, just slightly tweaked. So you should read through them all, but know that they're all super similar. All right, so we're talking about infinite limits here. Okay, infinite limits from the left is the first definition on the slide. We have a function defined for all values in some interval. If the values of f of x increase without bound, which means they increase forever, as the values of x, where x is less than a, approach the number a. So as we get closer and closer to a, our f of x's, our y's, get huge. They blow up, they increase without bound. Then we say that the limit as x approaches a from the left is positive infinity. And we write this. Sometimes we drop the plus sign and just write the infinity symbol. Okay, but we're talking about infinity in the positive upward direction. Okay, so if our graph increases without bound as you get close to a from the left-hand side, then the limit is positive infinity. If the graph decreases without bound, so drops real low, then we say that the limit is negative infinity. So an example, just a quick visual example of this, if this is my a right here, and my function I'm going to draw in blue, here is an example of an infinite limit. So as x gets closer to a from the left, the function blows up, it increases without bound to positive infinity. All right, and then the second one, make my grid again, and we're still approaching from the left. Let me label my a. We're still approaching from the left, and we drop down to negative infinity. It decreases without bound. So that's an example of positive and negative infinity. I'll scroll down, and you can pause the video to read through these other definitions, though they are very similar, just talking about limits from the right and then the two-sided limit. Now we have one example of this. Let me scroll down a little bit here. And in this one, it says that we can use a table of functional values and a graph. For this example, I just want to use the graph. And so what I have below, it's a little bit grainy, so I apologize for that. But this is the graph of f of x equals 1 divided by x. And let me draw my little arrows here. This graph continues on in all those directions. It has these two branches. It's not defined at 0 because f of 0 equals 1 over 0. That does not exist. But the question asks about the limit. The limit as you approach 0 from the left, and let's take a look. So here is 0, the origin. As I'm to the left of the origin over here, my function's here, down here, and it looks like I'm decreasing, and use the fancy words, I'm decreasing without bound. I'm decreasing downward in a negative direction forever. And what that means is that this left-handed limit is negative infinity. As you approach 0 from the right, so this direction is from the right, it looks like my graph is increasing without bound. And so that means that my limit is positive infinity. And for part C, what is the limit as x approaches 0? There's no plus or minus sign. That means the two-sided limit. Because our A and B answers are different, the two-sided limit does not exist. Does not exist. Now, this is our last slide of this section. I've labeled it as, quote, a fun one. You can feel free to disagree with me. I really like these types of questions. The graphs, there's no algebra to do, but there is a lot of visual understanding. Okay, so let's run through each of these. We have to evaluate one-sided and two-sided limits just by looking at the graph. So for part A, I'm just going to write down my answers and put commas between them. If you want to try them on your own first, please pause the video. The first one, -4 from the left. Here's -4. Here's from the left. It looks like the y-coordinate gets closer to 0. So my answer is 0. The next part, -4 from the right. Here's -4. This is from the right. It looks like the graph gets closer to 0. This one is -4, the two-sided limit, because my answer was 0 and 0. The two-sided limit is 0. And, hey, by the way, at exactly -4, it just passes through that line. That one's 0 also. Cool. Our answer to part A of this problem is 0, 0, 0, and 0. When you go to -4 from the left, from the right, the two-sided limit, and the actual function value, they're all 0. All right? Not going to be that way for all 4 parts of this problem. Change color for part B. All right, now we're looking at -2 from the left first. Here's -2. From the left is in that direction, and it looks like we're up at +3. From the right is that direction. That's the next part. -2 from the right. Looks like we're up at +3. -2, the two-sided limit. Got the same answers for the first two, so that's also +3. And then f of -2, where's the function at exactly -2? Do you see a filled-in circle? I don't. Does not exist. Part C. Now we're looking at +1. +1 is this guy, right? Oop, let's change color. +1 is that guy right there. First, it's +1 from the left. Okay, so hopefully my other marks on this graph aren't too confusing. Here's +1. Okay, from the left means that direction. So where is the graph up there? It's way up here at like 6, right? +1 from the left is moving in that direction, getting closer to 6. +1 from the right, that's this one up here. +1 from the right, looks like we're approaching 3. The two-sided limit at +1, because we got different answers for the left and the right side, the two-sided limit, DNE, the two-sided limit does not exist. But what is f of +1? Where's my filled-in circle? There it is. There's my filled-in circle. At exactly 1, we are up at exactly 6. Okay, last one. Let's go to yellow if it doesn't look too terrible. Yeah, I don't like yellow, so let's try a different color. How about black? D. Sorry, that looks messy, but that's okay. Now we're looking at 3 for D. The limit as we approach 3 from the left. Here's 3 from the left. Looks like we're going down forever. Decreasing without bound. 3 from the left is negative infinity. 3 from the right. 3 from the right. This is the right side of 3. 3 from the right looks like we're going down forever to negative infinity. Hey, did I get the same answer for both of those? That means that my two-sided limit is negative infinity. All right, this is an important one. We haven't really talked about this yet. F of negative 3 does not exist. Is there a point, a coordinate, negative 3 comma something on this graph? The answer is no. It's not positive 3 comma negative infinity. That's not a point. Negative infinity isn't like a number that you can plot. It's just where the graph goes down forever. All right. So if I went through that one too quickly, let me know. I can explain it more thoroughly. I can write it out more clearly. If you didn't catch all that, go back to earlier in the video, give it a listen again. Let me know if you have questions about this topic. This is our first true legit calculus topic. So now we're getting into the new material. Please let me know if you have any questions. Start working on this homework section 2.2. Let me know if you run into problems on the homework that you can't figure out. Happy to help you with them. Thank you very much for listening. Have a wonderful day.